Hey, good morning, 8th grade. Welcome back for another lesson. We're looking at problem 4.3 today, and I decided to get outside today. It's just a nice, beautiful morning hanging out here in my backyard. Got lots of orange trees, and hopefully my dog and our bunny won't bug us too much, but that's our plan for today. We're gonna be looking at problem 4.3, generating patterns, looking at linear, exponential, and quadratic functions. Let's take a look. All right, here it is, generating patterns. In this problem, you are given two data points for linear, exponential, and quadratic relationship. You will use these points to find more data points. Then you will write an equation for each relationship. All right, so we have to go back and really remember some of the details of what we know. So before we do anything, we're gonna need to make this kind of table in our notes, okay? So it says the first two rows in a table of numbers are given below. Write 4 more numbers in each column to make a linear relationship, an exponential relationship, and a quadratic relationship. So at this point, why don't you go ahead and pause your tape or pause your video, and we'll make this in our notes. Let's do that now. All right, here's my table that I made. You can make something like it. If you want to see it and pause it and take a look. But before we start, we have to really go back and remember how each of these patterns progress or how they go. Linear functions, if you recall, when we're going down for every value of x, the value of y is going to increase at a specific rate, like it's going to be plus this, plus this, plus this, plus this. Exponential functions, we're going to be dealing with some kind of connection related to the way that each value moves. And what we did is we actually would find one value divided by the value before, and that became our growth factor or decay factor. And then quadratic functions deal with something being taken to the second power and working its way through. So that's what we're going to start off with first. All right, so for linear, what we're going to do first is we look at this process of understanding this idea that when I go from 1 to 4, that's going to be a pattern that we would see in linear. It'd be plus something, plus something, plus something. So if I go 1 to 4, it's a plus 3. So the idea is if I go from here to the next one, it's going to be another plus 3. That would, in fact, in this case, need to be 7. And you can see that we continue that pattern all the way, plus 3 and plus 3 and plus 3, all the way down. We're going to be getting 7 plus 3 is 10, 10 plus 3 is 13, and 6 plus 3 is 16. And that's the pattern we're going to see specifically when it comes to the linear situation. When we're looking at the information for exponential, we need to make sure we remember that that means this number times something gives me this, and times something, and times something, and times something. But what we did is we actually realized, well, if we took this number divided by number 4, if we did 4 divided by 1, we know we would get 4. And that 4 is what we would call our growth factor. So basically what we're doing is we're coming this way, and we're doing a times 4. And from here to here is going to be another times 4. So that would be, in this case, you see we do 4 times 4 is going to give us a 16. And again, from here, we'd have a 16 times 4, which if I do that here, 16 times 4, okay, it's 16 times 4 is going to be 64. And again, that times 4 pattern is going to go all the way through. So then times 4 and times 4. So if I do 64 times 4, 256, and then 256 times 4, 1024. When it comes to quadratic, we haven't played around with this a ton, but we know that something happens if I plug the value of x in, something happens mathematically to have it become this one here. So 2 is going to become 4. And so if you recall, quadratic is signified by having the x value to the second power. If I look at 1 to the second power, I get 1. 2 to the second power, I get 2. So basically, it's going to end up being the same thing here. 1 to the second power, 2 to the second power, 3 to the second power, 4 to the second power, 5 to the second power, and 6 to the second power. And so that's going to give us our answers of 9 and 16 and 25 and 36. So that's our table following that specific data in that process. So remember, linear, it's going to be adding that rate Exponential is going to be multiplying times that growth factor, and quadratic is going to be just taking that value of x and squaring it in that case. All right, part B. Explain why the pattern in each column is correct. Okay, so if I look back at the same process here, we need to understand that linear. We know that linear structure, we've actually already said it, but linear is going to have a constant rate being added. So you can see we've got a plus 3, plus 3, plus 3, plus 3, plus 3. So we know that that slope is going to end up being 3 in this case, or that rate, or that growth factor, or sorry, the scale factor, the constant proportionality is going to be 3. So we know that's correct. When it comes to exponential, we know there has to be a growth factor of some kind, and this is growing by that constant multiplying of times 4, times 4, times 4, times 4. So we know we're correct there. And lastly, in this case, we know we're correct for the quadratic because, again, because it's to the second power, x to the second power is going to be in that structure of that equation. So we'll have x to the second power is going to be this all the way down. So each number is actually taken to the second power. And in this case, what we have is because we have one value of x going in, we get one value of y for each one, and nothing is repeating. All right, C1. Write an equation for each relationship. Explain what the information and the variables and numbers represent. Okay, so first thing for linear. In this case, I know that I'm going to be working with this rate of going to be a 3. So I know for sure that my slope is going to be 3. We have that process totally aware. But what we do need to also know is that we have to find out our y-intercept. And so far, our equation for this one would be y equals 3x. But what we would do is we would actually go back and figure out, well, what if I put in a 0 for this? If I put 0 back here and I placed 0 up above, notice how what would happen is I would go back 3 the other direction. So since I'm plus 3, I'm going to go minus 3 in this case. So that means that the value going the other direction would actually be minus 3, which would give me a negative 2 in that case. So what that would do is that would give us our equation specifically being y equals 3x minus 2. And that's our case for the linear situation. All right, when it comes to the exponential function, we have to make sure we remember the overall structure here. This is a key part. So if we remember that we're always going to have y equals this a times b to the x power. Remember that this a is our y-intercept, b was a growth factor, and x was here. So we can't forget a equals the y-intercept, and b is our growth or decay factor. In this case, it's growth because we have a growing process there. Now remember, what we always would do is we would need to figure out what the y-intercept was in this case. We already know that it's 4 for part of it, so we have that piece. But what we need to do is remember that we have that 0 plugged in. We have to figure out what would it be for 0. We did that for the linear situation. So remember how we're multiplying by 4. We would do a division by 4. So if I came back and I actually did that same work, and some of you might already know the process here, but if I did 4 divided by 4, or sorry, my mistake, 1 divided by 4, right, because we're at 1, going back that way, we get our 0.25, or 1/4. And that turns out to be our y-intercept. And so in this case, the y-intercept is actually going to be, if y is equal to 0.25, or 1/4, times 4 to the x power. And let's test that to make sure we're doing it right. So if I have that, if I come in here, I'm going to do 4, oops, let's go this way. So 4 to the first power equals times 0.25. There we go, we get our 1. Okay, let's try another one here. I'm doing 4 to the second power equals times 0.25. There we go, so we got our 4. I know it's been a little while since we've done this, but hopefully you're remembering. Let's just test it all the way down. So I'm going to have here my 3 to the, or sorry, my mistake, we did it again. 4 to the third power, I'm putting that 3 in, equals, but then I do times 0.25, and there's our 16, so that works in that case. So our equation specifically here for this one is that. Now some of you also might remember though, we could also do the y equals 4 to the x minus 1 power. We did that with our work with the the rubas and the king and Monterect and the peasant and all that stuff. So either of these options would work, okay? All right, lastly, quadratic function. Well, we kind of already did this one in this case. We already know that like we have this x to the second power up here. So if I have x to the second power gives me that 1 second power, I get this the whole way down. So it turns out that that's all we have. Our y is going to be equal to x to the second power. And that's all that we really need to do in that case, understanding that process. So we really have to understand the differences here of each of these. The linear function still follows that slope-intercept form. And then we have this overall structure here. Make sure you remember this, make sure you remember this. And this is no matter what's going to have something to the x power in this case. So we don't miss those parts. Well, looking at part 2 here, we can't really work with our classmates in this case to all the same equations. Well, I don't know, you should have the same equations for the linear and exponential. There are other options for quadratic, and there are 2 other options which you could have. For those you're going in a little bit deeper, trying to figure that out. But what properties of each kind of function help you construct the table? Well, I think what we know is that understanding the details of the structure of those functions, we can't forget the way those look. It's going to be really important that we don't miss those parts. All right, that was a little bit of a quick one. Hopefully it made sense. We definitely need to make sure we understand the different structures of all the functions that we've seen over the course of the year when we get to 4.4, because we're really doing a big review of everything. We're going to go back and talk about all the way that the wording looks a certain function type, the table looks like a certain function type, the actual equation looks a certain way, and then with the graph looks a certain way. We'll tie all that into problem 4.4. But this is a good review for us to get ready for that. But hey, let's look at the ACE work today for this particular problem. We are going to be working specifically on problems, or ACE work 8 through 10. So let's take a look at that. All right, question 8. The table below represents the projected growth of certain species of deer. Use the 3 tables to answer parts A through C. So you have a table 1, table 2, and table 3. Look what it says. Describe the growth represented in each table. Do any of these patterns represent linear, exponential, or quadratic? So look really careful at the data. See what they look like following that pattern there. Write an equation for each of those that represent linear, exponential, or quadratic. And does any table show a population of deer growing at a rate of 3% per year? Don't forget what things grow at percentage rates, what pattern that does, okay? All right, let's look at number 9. Very similar situation. The Department of Natural Resources collecting data on 3 different species of animals. They find that the species show different patterns of population growth. They write the equations below to represent the population P of each species after T years. So you have species 1, species 2, and species 3. Don't forget the structure of the functions, and they're giving you clues right away to what it's looking like. So look at that, describe what information the numbers and variables represent, describe the patterns of growth, and pick any 2 species. After how many years will the populations of the 2 be equal? So you pick 2 of these and figure out when they'll be equal. And then number 10, suppose the figures shown are made with toothpicks. So you have figure 1, 2, 3, 4, and 5. What patterns do you notice in the set of figures? So you have your figure 1 is going to be your X, and the total of toothpicks is going to be your Y. So how many toothpicks make figure 7? Is it linear, quadratic, exponential? All this information. Got perimeter questions and then toothpick questions, and then write an equation for figure N, and then write an equation to represent the total number of toothpicks needed to make figure N. So all that work is there. All right, guys, hopefully that was a smooth one. We'll talk more about the process of what's coming up in our Google Meets, but other than that, hope you guys are doing well, and I look forward to seeing you as soon as we can. Take it easy. Bye.